Today I'm going to talk about a surprising synergy between classical and quantum mechanics that I believe will help students understand both of them. And this is work that is supported from the Air Force Office of Scientific Research. When we teach classical mechanics and quantum mechanics, even though we often say you can't learn quantum mechanics without having classical mechanics, they seem pretty unrelated, with a vague and incorrect notion that the two should agree for large quantum numbers. We also have some very odd sounding quantization rules that come from Dirac, such as take a Poisson bracket, which often isn't taught very much in undergraduate classical mechanics, and replace it with a commutator. So the real connection between classical and quantum mechanics is often not a very strong one, particularly when students are initially starting out. I'm going to give you two examples of a new connection between classical and quantum that I believe will help students gain intuition about how the two are connected. The idea for this comes from a source that you might not have thought of as being one that would be connecting classical and quantum. It's the 1930 textbook Elementare Quantenmechanik by Born and Jordan. Here's a picture of Born and Jordan. And when they talk about the harmonic oscillator, and this is a picture from the book, they have these two lines in them. Let me get my laser pointer here. They take a combination of P with Q, and they find when they look at the equation of motion of that, the time derivative is proportional to the object. So this is a way that you have decoupled the differential equations that you've been working with. And this is actually a well-known mathematical technique for solving coupled linear differential equations with constant coefficients. But I'm going to show you in this talk, the idea actually goes much further than just focusing on differential equations with constant coefficients. All right, so let's go into detail about how this works for the harmonic oscillator. So in the conventional approach, we start from the equation of motion. These are officially the Hamilton equations of motion, but you don't need to know anything about a Hamiltonian to recognize that these are the proper equations of motion for a harmonic oscillator. We have that x dot is p over m. You can think of that in essence as a definition of the momentum. And p dot is minus m omega squared x, where omega is the oscillator frequency. The way that we solve this is we take a second derivative of this first equation here. We get x double dot is p dot over m, and then we substitute in what p dot is to get minus omega squared x. You then can solve the differential equation, and in an undergraduate class, particularly a first-year class, you will get them to recognize that the solutions are sums of cosines and sines, and when you work out the particular constants, you will get x0 cos omega t plus p0 over m omega sine omega t. You also could do this with complex exponentials, but certainly in a first-year class, this is not done. Complex exponentials don't seem to be introduced in classical mechanics courses in the US until you get to the junior level classical mechanics course. And in some cases, maybe not even there. If you do use the complex exponentials, then you often have to tell the students to take the real part of the solution at the end when you're getting your final answer. And when looking at this, there's no obvious connection to quantum mechanics. So let me show you the new approach. In the new approach, we start from the exact same equations of motion, but we do what Born and Jordan did. We take a linear combination of the two. At the moment, I don't know exactly what that linear combination should be, so I'm going to call it alpha. And then we take the time derivative of A, which will be p dot plus alpha x dot, and we force it to be proportional to A. So first I have to substitute in with the equations of motion to get minus m omega squared for the p dot and alpha p over m. Now, if I want to force it to be a number times A, the coefficient of the p term is the thing I have to factor out. So I'm going to factor out alpha over m, and I will get p minus m squared omega squared over alpha. If I want to force this to be in this form, this coefficient must equal alpha. That's pretty simple to do. I just have alpha equals minus m squared omega squared over alpha, where when you solve that, you find alpha is plus or minus im omega. For the A object, we're going to be taking the minus im omega, and then there'll be a similar one that we call A star, which is the complex conjugate of it, that will work with the plus im omega. So what we find using alpha over m, you see alpha over m will be plus or minus I omega. We get A dot is minus I omega A dot star is I omega A star. Both are solved by complex exponentials. It's one of the easiest differential equations you can solve. A of t is A0 e to the minus I omega t, and A star is A0 star e to the minus I e to the plus I omega t. And then when you look at what A is, you set its initial values to be P0 plus or minus im omega x0. So for A0, you'll get P0 minus im omega x0 because we chose alpha is minus im omega for the A object or the A function. Okay, so we've solved the problem. Now, if we want to find x, we just solve for x. In order to solve for x, we have to take A star and subtract A from it. So A star is P plus im omega x, and A is P minus im omega x. If I take the difference and divide by 2 im omega, I will get x. And it's a fairly simple algebraic exercise using this A0 to find that you get x0 cosine omega t plus P0 over m sine omega t, exactly the same as before. Now, the next thing that you can do with this is you can look at energy. And I'm just reminding you what the A and the A star are. To get the energy, we look at the product of the two. A star times A divided by 2m. So 1 over 2m mod A of t squared. You can see that's going to equal P squared over 2m plus 1/2 m omega squared x squared. Because I take the square of the real part and I take the square of the imaginary part, add them together, and then I'm dividing by 2m. But I also can evaluate it from this form. And when I evaluate it from this form, because e to the minus I omega t times e to the plus I omega t is just 1, I'll get mod A0 squared. And mod A0 squared is just P0 squared over 2m plus 1/2 m omega squared x0 squared. That's a constant. And we're going to call that constant E. And you see, that's how you derive energy conservation. It's super easy to do using this technique. But there's more. Now we actually can make a connection with quantum mechanics. And this is what Born and Jordan did in their 1930 papers. So let's talk about the quantum harmonic oscillator. How do we introduce quantum mechanics? Well, we have to introduce the canonical commutation relation between x and p. So commutator of x with p is IH bar. We're going to just make A into an operator by elevating P to an operator and X to an operator. That's the most natural thing to do. And we're going to compute the energy, which should be the Hamiltonian. So we're going to compute 1 over 2m A dagger A. And by just using those definitions for the A and the A dagger, again, I will get a P hat squared over 2m. I will get a 1/2 m squared omega squared x hat squared over 2m. That's from the squares of each of these terms. But now I have a cross term because p and x don't commute. And if you carefully work out the sign, you can see it's minus im omega commutator of p with x. Now, commutator of p with x is minus IH bar. So when I evaluate that commutator, I get 1 over 2m A dagger A is p squared over 2m plus 1/2 m omega squared x hat squared minus 1/2 h bar omega. I just have to take this term, move it to the other side, and I will have the Hamiltonian for my quantum system. So this form of working with this A object has this natural connection to quantum mechanics, and it gives you can derive the quantum Hamiltonian in the same form as the classical Hamiltonian with a quantum correction, which in this case is the 1/2 h bar omega, and it's a constant. It's a quantum correction because if I took the limit h bar goes to 0, that term would disappear. And in the classical case, my energy was just given by this expression without this extra term. But of course, we know in quantum mechanics, the extra term is needed. And by following the exact same kind of logic as we did, just changing the position and momentum into operators, we're able to get this to work in the quantum case. Okay, so now I'm going to move on to, so as I summarized, this A object or A function provides the seamless connection between classical and quantum mechanics. And I think it's a really nice example to show people, particularly when you start showing them the operator technique for the harmonic oscillator, to make it clear that what you're doing actually has a nice connection back to classical mechanics. Now, this is not a one-off coincidence. It's actually a general result, and I'm going to illustrate it again for you now with Kepler orbits and hydrogen. So let's go back to the conventional approach for gravitational orbits or planetary orbits. We have four equations of motion now. R dot is PR over M. We have PR dot is P theta squared over MR cubed minus K over R squared. K is going to be the constant in the gravitational attraction. Theta dot is P theta over MR squared, and P theta dot is equal to 0 because it's a central force. So because P theta dot is equal to 0, that means the angular momentum is conserved. And we can write L, which equals MR squared theta dot, which is P theta, is equal to a constant. And then I can take that L and substitute it in here as a constant. Then we focus on the radial equations of motion. We're going to differentiate this equation. R dot will be PR dot over M. We replace in what PR dot is using L squared for the P theta squared. You get this form here. And now what we recognize is if we multiply this by R dot, we'll get a perfect differential on both sides. This is the differential of 1/2 R dot squared with respect to time. And then this term, if I integrate it with respect to R, because I multiplied by an R dot and I'm integrating dt, but the dt's then cancel, I can integrate dr. This is a perfect differential that I can integrate as well. And so from that, you get energy conservation. The constant that comes out of the integration is the energy. And then you get these other terms that contribute along with the kinetic energy to the total energy. We then solve for R dot, which we're going to rewrite as dr d theta theta dot. And then using the fact that theta dot is related to angular momentum, we bring in an L over mr squared. And then that is equal to the square root of this. So square root of 2e minus this. And now what we're going to do is we're going to rearrange it and integrate it. So we can get an integral d theta is integral dr L over mr squared 1 over this square root mess. This looks like something that would be impossible to integrate, but it actually has an exact integral. The integral of d theta will give me theta. The integral of this is minus arc cosine of this mess. And if I take the cosine of both sides and then solve for this 1 over r, you then get the orbit equation. 1 over r is mk over L squared, 1 plus the square root of 1 plus 2EL squared over mk squared cosine theta. That's the well-known equation of an ellipse with the origin at one of the foci of the ellipse. All right, let's take a look at the new approach. How does this work? We start the same way, equations of motion. We recognize angular momentum is conserved. We are now going to decouple, but now we have to decouple with a function. And the functional form that we need to use is alpha over r plus beta. I'm not deriving it for you at the moment here, but I will show you how this is derived a little bit later in the talk. All right, so what we do again, we differentiate, and then we choose the alpha and the beta to make it work. So when we differentiate, we get a PR dot minus alpha over r squared r dot. The beta term doesn't contribute. We then substitute in for the PR dot, and we substitute in for the R dot. We get L squared over MR cubed minus KR squared minus alpha over M squared PR. The coefficient of the PR is the thing that I have to factor out if I want it to be proportional to A. So we factor that out, and we're left with a term that is linear in 1 over R and has a constant term. So to force it to work, I have to have this object equal alpha. You can see that's going to hold if alpha is plus or minus IL. Once I have alpha, I plug it in here to get beta, and then I also get the coefficient in front. So what you find is alpha is plus or minus IL, beta is minus plus IMK over L, and A dot is minus plus I theta dot A. This is a super easy differential equation to integrate. We're going to work with the minus sign. So we're going to be picking alpha is plus IL. That's the thing that we're going to call A. And if we integrate this, we will just get A0 e to the I theta. And then the A star will be A0 star e to the minus I theta. It's as simple as that. Now, how do I get the orbit? To get the orbit, I have to go back to the definition of the A and solve for 1 over R. But before I do that, I have to determine what the A0 is. So to find the A0, we work at the point of closest approach. At that point, there's no radial momentum, so that term is 0. And at closest approach, R will equal R0, the distance of closest approach. And so A0 takes this form. Notice that it is purely imaginary. So now to solve for 1 over R, what we do is we take, again, A minus A star divided by 2IL. That will give us 1 over R minus MK over L squared. You can see that here. If I take this minus its complex conjugate, the PR term will disappear. I will get twice this term. And then if I divide by 2IL, I'll get 1 over R. And if I divide by 2IL, I'll get minus MK over L squared. When we substitute in what A minus A star is from the form here, because this is pure imaginary, it just becomes twice the object. When I divide by 2IL, I will get a 1 over R0 minus MK over L squared. But it's also going to be multiplied by e to the I theta plus e to the minus I theta, which is a 2 cosine theta. And the factors of 2 will cancel, and I'm left with this. Now, all I do is I solve for the 1 over R, and you see I've got the orbit equation. Now, you might say, well, this doesn't look like the coefficient you had before. Well, you can fix that by using the energy as L squared over 2m R0 squared minus K over R0. And you can show then that this coefficient is actually equal to the square root of 1 plus 2EL squared over MK squared. And so it gives the exact same orbit equation. But it is a much, much simpler derivation. The most complicated differential equation I have to solve is A dot is equal to plus or minus I theta dot A. And the solving for R is like really simple. It's just a linear equation I have to solve to get 1 over R. All right, let's take a look at the energy. Working off what we did with the harmonic oscillator, we're going to look at 1 over 2m A star A. Of course, using this form, that's going to be 1 over 2m A0 squared because the e to the I theta, e to the minus I theta will cancel out. When I take the mod squared of this term, I'm going to get 1 over 2m PR squared plus an L squared over R squared minus 2m K over R from the cross term, and then an extra constant m squared K squared over L squared. And this must equal a constant. We're going to call that constant E plus m squared K squared over L squared so that you get E is PR squared over 2m plus L squared over 2m R squared minus K over R, which is just mod A0 squared over 2m minus this extra constant term that we found. Okay, so energy conservation is simple as well. Now, how do I do the mapping to hydrogen going into quantum mechanics? It's the same thing as we did before. We now introduce the quantum commutator, canonical commutation relation between the radial operator and the radial momentum. Commutator of R with PR is IH bar. We elevate A to an operator, PR hat plus I over L R hat minus IMK over L. L is a number here, not an operator. And I'll show you why that comes out as we complete the derivation. All right, so the Hamiltonian should be related to 1 over 2m A dagger A. So we just compute that. We get the terms that we had in the classical case, the PR squared, the L squared over 2m R squared, the minus K over R from the cross term, and the constant term. But we get an additional contribution from the commutator. It's a minus I PR commutator with L over R hat. This is a commutator that you can work out rather straightforwardly. It is equal to, this commutator will equal L times IH bar over R hat squared. And so you're going to get a minus H bar over 2m R hat squared times L. So it actually combines with the term that we already had of L squared over 2m R squared. And we still have this constant term left as well. Now, to make the correspondence with the quantum mechanical solutions, we have to let L equal h bar times L plus 1 with L an integer. And we have to use the hydrogen value for the coefficient, which is k is equal to e squared over 4 pi epsilon naught. And then what you find is the Hamiltonian for a fixed angular momentum for hydrogen will equal 1 over 2m a dagger a plus el, where el is minus, this is again k over 2, and if you work out with the constants, it becomes minus e squared over 8 pi epsilon naught a naught L plus 1 squared. That is the exact quantum mechanical energy levels for hydrogen, with A0 being the standard relation for the Bohr radius. So everything from quantum mechanics comes out in the same way, and you have this very nice connection between classical and quantum mechanics when you're working with solving the radial equation for states that have definite total angular momentum quantum number h bar L. The only thing that's a little bit odd is we had to set the L, the classical L, to h bar L plus 1 in order to make this work. You might have thought we wanted to set it to h bar L, but it has to be set to h bar L plus 1 in order to get this to work. Oh, I also should point out that we changed the potential. So the classical potential, if I go back one slide, the classical potential is this part here. That's the classical effective potential. But the quantum one has this with an extra term, which vanishes when h bar goes to 0. So there's, again, a quantum correction to the classical potential for problems that are related in this fashion. All right. So the simplified treatment of this classical orbit also provides a neat connection to the quantum solution. And I think that this is really pretty cool. I also think it's a very nice way of introducing both of the topics that that we like to teach to juniors and seniors. I think it's a much nicer way of doing the orbit equation. And it's very nice to show this interesting connection between classical mechanics and quantum mechanics that just falls out by simply quantizing what the classical calculation is. Okay, one question you might ask is, how general is this? Well, I'm going to hopefully convince you that it is very general. So what we're going to do is we're going to consider a one-dimensional classical system with a potential v of x. And the equations of motion for that are x dot is p over m and p dot is minus v prime of x. We want to decouple it with an a equal to p minus I w of x. If I take the time derivative of this, I get a dot is equal to p dot minus I w prime of x x dot. I can then use these equations of motion to substitute in. I get minus v prime of x minus I w prime of x p over m. Remember, I have to factor out the coefficient of the p to get it to be something times the a. So we factor out coefficient of the p, and we get p minus I m v prime of x over w prime of x. I have to set this equal to this in order to make this work. And what that requires is that w of x is m v prime of x over w prime of x. I move the w prime over to the other side. I recognize I have a perfect differential that I can integrate. So you'll get 1/2 w squared of x is equal to mv of x plus c. In all of the cases that can be exactly solved, we can find a c such that this is a perfect square. And then I can just take the square root of it to give me the w. Whether or not this would still work for any c that you might want to pick is something that is worth investigating further. We haven't looked into that in too much detail. But under the assumption that this is a nice perfect square, then w of x equals plus or minus the square root of this will be a simple function of x with no radicals in it. Okay. We can now relate this to quantum mechanics. What we found classically was a dot is minus I w prime of x over ma, when a was equal to p minus I w of x, and 1/2 w squared of x was equal to mv of x plus c. So we now just quantize everything exactly like before. We're We're going to calculate 1 over 2m a dagger a. We're going to get a p squared over 2m. We're going to get a w squared over 2m. And then we're going to get the commutator term, which is minus I over 2m commutator of p with w. You can evaluate that commutator. You get minus h bar over 2m w prime of x. We now want to use this relationship here. 1 over 2m w squared of x is equal to v of x plus c over m. We can plug that in. We get 1 over 2m a dagger a is p squared over 2m plus v of x plus c over m minus h bar over 2m w prime of x. And again, what you see is happening is we get the classical potential plus a quantum correction, and oftentimes we also get a constant in addition that is coming in. Okay, so this classical quantum correspondence that we're looking at is relating problems that have slightly different potentials in the quantum realm versus in the classical realm. So what we like to say is that the quantum system has this quantum corrected potential relative to the classical system. And now what we can do is quantum mechanically, we can move that constant over to the other side. And now look at the equation of motion. A dot is IH bar commutator of H with A, which will be IH bar over 2M commutator of A dagger with A times A. We can work out what the commutator of A dagger with A is. It is, and when all the dust settles, you find it's minus I H bar squared over M W prime of X A. Now the classical one was A dot is minus I W prime of X over M A. And aside from this extra factor of H bar squared, you can see these two equations have exactly the same form. So the classical quantum correspondence that you get by proceeding in this fashion is that at the operator or function level for the classical mechanics, the equations of motion for the object that decouples the dynamical equations are exactly the same form. In order to have that, you actually have to have different potentials in the two. And I think an interesting question is, how useful is this classical quantum correspondence? It's very different from the standard way that we teach it via Ehrenfest theorem, where we work with the same potential for the quantum system as for the classical system. But that correspondence has a lot of issues with it that I don't have time to go into in great detail here. Okay, so we are currently looking at how this works for driven and damped systems, and there's no reason to think that this shouldn't work for those systems as well. And that will also provide, I think, a very nice, interesting correspondence that will be actually very interesting to introduce into undergraduate classes. We almost never talk about damped systems in quantum mechanics, but in the new second quantum revolution, decoherence and damping is an important topic. We should be bringing it into the classroom. And if we have an easy way to make this correspondence via looking at the classical damped oscillator and seeing how it maps onto a quantum system with dissipation, that would be a really interesting thing to be able to teach in an undergraduate classroom. So thank you, Boren and Jordan. This simple insight that you have leads to a much deeper relationships, which may provide a new way of thinking about classical and quantum correspondences. And for sure, it gives a nice and a clear way to relate classical dynamical solutions to quantum solutions via this factorization method. And I want to thank the collaborators on this. Leanne Dowdy is a professor at Georgetown, and Jason Tron is a graduate student in the physics department. And I will end there. I ended up managing to do it with 29 minutes and 20 seconds, so that's pretty good. You guys have any questions about it?